You can see my ugly face when I'm doing this. Now look at I told you there were 3 parts to this chemistry. We're going to have like a theme, and the first part was about reactions, whether it happens, whether it occurs. That was thermodynamics. We figured out delta G. Does the reaction happen? Is it spontaneous or not? That was good. Well, just because it was spontaneous didn't mean it was a good reaction to occur. Because it's spontaneous, if I look up the delta G of diamonds burning, it's spontaneous. Wouldn't want to do it, not just because they're expensive, but because it's very slow. Diamonds are forever, supposedly, and of course it takes a long time for a diamond to turn into carbon dioxide. All right, so we had to look at how fast the reaction happened. Well, this is the crazy part. This is what we're going to spend the next 3 chapters on. Just because the reaction happens, just because it happens fast, a split second, doesn't mean it's necessarily what I'm going to want to do, because of what's called the equilibrium. Turn that light off for a second. Let me show you something about equilibrium. You don't have to copy this down yet. I'll show you a little animation and a little analogy. I used the analogy last year. Okay? I'll start with the analogy before I do the animation. The analogy is this. I said, you may remember this. I hope you do. We were talking about gas equilibrium and phase equilibrium between solids, liquids, and gases. And my example was, it was in the spring, and I was using PennDOT trucks working on a road. And I said there was 2 piles of bricks and 2 crews, all right, working on the road. There's a pile of bricks on one side, a pile of bricks on the other side, and there were 2 foremen. And one foreman says, you know what? It's silly to have 2 piles of bricks. He says to one of his workers, he says, hey, Stan, take these bricks over to the other side, make one big pile. Meanwhile, unbeknownst to him, the foreman on the opposite side says, hey, it's silly to have 2 piles of bricks. Stosh, take all these bricks over to the other side. So all day long, Stosh and Stan walk back and forth, carrying 2 bricks, pick up 2 bricks. Stosh and Stan, they're classic Polish names. We use them all the time because they're not very bright. And I'm Polish, so I use Polish names. So Stosh and Stan walk back and forth. Hey, how you doing, Stosh? Good. Stan, how's the kids, the wife? Great. 8 hours they work. Assuming they walked at the same pace and each picked up 2 bricks each time, what happened to the pile of bricks? They stayed the same. That's equilibrium. That's actually dynamic equilibrium. You have a constant change. They're picking up different bricks each time. They're constantly moving, but the piles are staying the same. All right, now that was for phase equilibrium. You may remember phase equilibrium was, remember I did stuff like this? You didn't like it, by the way, and it took a while to get used to it, but it was, hold on. I didn't want to kill myself. It was this. Remember this? I drew syringes, and we used syringes, okay? And I said we had some water in the bottom of the syringe, and I had some vapor, and I have evaporation and condensation. You remember doing these? Yeah. Okay, and I said, what would happen if I pushed down on the syringe? What would happen if I pulled back on it? What would happen if I heated it? What would happen if I cooled it down? Increase the temperature, decrease the temperature. We did all that stuff. Volume, pressure, and temperature changes. And we said, well, gee, will it make it evaporate more, or will it make it condense more? That was equilibrium, because at equilibrium, the rate of evaporation was equal to the rate of condensation. And it took me like a whole chapter to teach this to you, to get you used to the concept of equilibrium. Now it's going to be much harder, and here's why. Not only do I have to understand what equilibrium is and predict whether it's going to favor evaporation or condensation, I got to be able to do actual calculations with it. All right, but before I get to that, which will be soon, let me just show you a little example now, not of phase equilibrium, but of chemical equilibrium. Say I've got A plus 2B equals AB2. All right, A is red, B is blue, and when they get together, they keep the same colors, but they're linked together in my little animation here. All right, if you watch, in reality, what's happening is things don't just go one direction. I don't just get A plus B yields AB. But if you watch any of these guys, every now and then a guy's breaking up, and every now and then a guy's coming together. All right, this guy just came together, but he'll break up as well. And that happens. In real chemical reactions, you have a forward direction and you have a reverse direction. Okay? Both of which can occur. I kind of lied to you. You know, most of the time when I gave you guys reactions like sodium plus chlorine yields sodium chloride, which was like my classic example I used pretty much every time I did it first day of an example, and we balanced it, I always drew an arrow that went one way. You know, sodium gets together with chlorine and makes sodium chloride. All right, and that was it. And we didn't talk about the fact that sodium chloride might be able to break up. And in most reactions we did in Chem 1, I hate to tell you, they were one way. So that was okay. It was okay to simplify things. Most of the reactions in reality are like, whoops, like this. They're like that. They are constantly coming together and breaking apart, forward and reverse. And that's what we got to take into account. And that's what's going to make this a little bit more difficult. Now, it's going to start out, I think today's, like, who's leaving now? Katie was leaving. It's pretty easy. And it won't take you very long to do the homework. It's going to be pretty simple. But it's going to get complicated. You can probably see why. When I start putting numbers to this, calculations, concentrations, it's going to get more complicated. But let me first get the concepts across. Equilibrium, chemical equilibrium. What is it? And what can it do for you?
What can it do for us? Absolutely.
Well, that's true. Unless you're going to be a chemist, there's really not a whole lot of point to this. But
so what are we doing? Let's just go raise of hands who's actually.
Because this is actually a chemistry class.
Oh, come on.
All right, chemical equilibrium. What is it? It is basically two opposing reactions occurring simultaneously at the same rate. As I said, you could use the analogy of Stosh and Stan walking back and forth. All right, on the PennDOT road.
Trying to see how small the font can get.
Yeah, well, good point. Good point. I really should make that bigger.
Yeah.
By the way, I also you'll notice, if I haven't said already, I'm using a black background. I think I'm going to try to turn most of them into black backgrounds because it is a lot easier on the eyes when watching the videos.
You should bold.
But anyway, I will have to do some changes probably.
What's your obsession with black? black
I'm racist.
Black board?
We knew it.
Mm-hmm. All right, so two opposing reactions occur at the same rate, all right, simultaneously. It's called dynamic equilibrium because the reactions continue even at when it reaches equilibrium. It's not like they stop, okay? It's not like those two piles of bricks just stay exactly the same. I constantly have Stosh and Stan walking back and forth picking up different bricks. They're moving all the time. I constantly have guys getting together. And when it comes to, if you think back to the my syringe I was talking about with the vapor and liquid phases, same thing's true. Even in this, I have constantly, some guys are leaving and becoming vapor, and some guys are hitting into the liquid phase and becoming liquid again. You have a constant, it's just that the two are equal, okay? All right, so it's dynamic. Now, let's apply this. Here comes the example I'm going to use that's going to apply this to chemistry. Okay, because up till now, it was only phase changes or guys on PennDOT. All right, now it comes to chemistry. Watch this. I think when you're done copying this example down, you're going to see why we have to talk about this. Copy this as my example. A plus B, you'll see it. Spread it out. Especially spread out the different. Look here. Especially make a large enough space between B and C and make this arrow. Actually, the arrow should look kind of like this. All right. In reality, you're going to see an arrow that looks like this. I just didn't have the arrow to show that on my fonts or whatever, symbols. But in the book, it's going to look like that. It's going to be an arrow that's a double arrow. Right? Make sure there's a lot of space in between that because I want to be able to do something between B and C. Okay, watch what happens here with this. You may remember in kinetics, we started out with initial concentrations. Let's just say I have 4 moles of that and 4 moles of that. And initially I have no C at all. Right? Write that down. Well, remember this from kinetics? And again, it should be a nice big space between this group. We're going to fill that in with something. Okay? Nice big space between the 4 and the 0. We're going to fill that in when I'm done. After some amount of time x, let's say I now have 2 moles of A and 2 moles of B produced, or used up. Well, see how much you remember from kinetics. Because the first mistake we made in both classes when I asked this question was a mistake about how much C is going to be made. Okay? 2 plus 2 does not equal 4. How much C is made? Does not equal 4. It equals what? If I used up 2 moles of A, how much C did I make? Look at the stoichiometry. Look at the coefficients. 2, exactly. And here's the way, if you remember, back to kinetics, I did this. If you remember, hopefully you do. I did this back then. Why does 2 plus 2 equal 2? Because 1 plus 1 equals 1. 1 carbon plus 1 oxygen yields 1 carbon monoxide. So it doesn't equal 2, all right, because you're making a compound. All right, so either way, that was just a little review. Here's the big part about the kinetics we learned. you might think that after time 2x, we'd have 0, 0, and 4, right? But that didn't happen. Why not? What's happened between here and here to the rate? Yeah, it got cut in half because the concentrations are half what they were here. They're now, the rate is half what it was, right? So if I wait another time 2x, what am I going to have for concentrations now? 1, 1, and I'll have another 1 mole of C produced onto the 2 I already had. So how much C will I have? 3. Okay. You remember all this. And I stopped there. I stopped there because we were talking about kinetics. I just wanted to get that point across to you. That as the concentrations decrease, the rate slows down. I said it would approach. Remember, we even drew this. We just took the test. It would approach 0, right? Remember that? Okay. Well, here's the crazy part about this.
You lied.
I lied again.
Oh my God.
Yeah.
Hey, why do you get paid?
I know. After time 4x, 5x, 6x, time infinity x, if it's a reversible reaction, this is an infinity sign. Time infinity x, forever I could let it sit there. If it's a reversible reaction, I could very well end up with a situation where it never changes again.
Oh,
Now, it doesn't mean it never changes. There's constant change. But here's why this can happen. If you haven't figured it out yet, let me show you why. That's why I told you to leave this space here. Watch. In the beginning, I'm going to use 2 different colors. Okay? You guys just don't really need to do it, but I'm going to use 2 different colors. You ready? In the beginning, if this is a reversible reaction, and I have no C, is there any reverse rate happening at all? No. There's only a forward rate. I want you to make an arrow as long as possible between these two. Like that. Now, and there's absolutely no reverse reaction. After time x, I now have half the concentration of that forward rate. What will I draw for that forward arrow? Half is big, right? I'll make him about that big. Now, unfortunately, this is a reversible reaction. I now have some product. So that means there can be a reverse reaction happening here. So I'll use a different color. I'll use red. I now have some reaction happening here. Make it smaller than the green one, but visible. I've now used up more. Look here, time 2x. What's happened to the green arrow? It's gotten even smaller. The forward reaction is slowing down because I'm getting less and less reactants. What's happening to the red arrow, the reverse reaction? It's getting bigger and bigger because I've got more and more and more product. Until, at this point, look at the 2 arrows. They should both be the same size at this point. And that will happen in a reversible reaction. So that it never changes from then on. It always will remain those concentrations, even though it's constantly changing, like you saw a minute ago in that little animation. A and B is getting together with C. C is breaking up into A and B. Okay? Now that hopefully brings home to you. See how I'm using the concepts of kinetics. We learned just last time the speed of the reaction slowing down or speeding up depending on the concentrations. And the new concept of a reversible reaction resulting in what we get is an equilibrium. Now here's the crazy part about equilibriums. Remember I told you it's not enough to know whether the reaction occurs if it's spontaneous. Delta G is negative. It's not enough to know how fast. This could be a highly spontaneous reaction and happen in a split second. But if the equilibrium lies way over to this side, in other words, if the red reaction, the reverse reaction, is way bigger than the forward reaction, you know what you can do? You can put 4 moles of this and 4 moles of that in, and at equilibrium have 3.99 moles of this, 3.99 moles of that, and 0.01 moles of that. That's all you'd get from this reaction if the equilibrium were such that the reverse reaction was way better, way faster than the forward. Vice versa. If I get a reaction that the forward reaction is way better than the reverse, if I put in, say, I'm just using numbers like 4, all right, I could end up with just 0.01 moles of this, and 3.9 moles of that, okay? 2.9 9 moles of that, right? Okay? So that can happen. So how do you tell? You tell that by what's called the equilibrium constant, which I'm going to show you how to get and use over the course of the rest of the chapter. But before I do that, what I need to do now is this. Because I think everybody right now, look at your faces in the last period too, everybody seems to understand it, okay? And they do. But I want you to write it down, all right, in terms of, in your notes, so you understand it 2 years from now when you're taking this class. As the reaction, it's exactly what I just explained. I'm just putting into words. As the reaction proceeds, the concentration of the reactants decreases, and therefore it slows the forward rate. This is just to have it for your notes. I'm not putting anything on the board here I haven't already explained. And you can see that forward reaction decreasing. Meanwhile, the reverse rate is getting bigger. Meanwhile, the concentration of the products increases, thus increasing the reverse rate. Eventually, the two are equal, and you're at equilibrium. Stosh and Stan are working at the same speed. And that's illustrated both by those arrows and by those words and by my analogy with the pen dot and by the little animation you just saw. So I think everybody kind of understands this. The question is, can we apply it? And it is going to get confusing pretty soon. Not today, but pretty soon. It is going to get confusing when I start doing concentrations, plugging them in and calculating constants using this. So it's kind of important that we understand it first. I realized at the end of the day, last period, that I could have taught this entire, what I'm going to have you do for homework, in about a minute. I could have just said, okay, do this to get Kc. Well, that's what we're going to learn how to derive, Kc. And it would have made you get the answer just as easily or better than having gone through all this. However, I am going to go through all of what I'm about to do here, including the derivation of Kc. Okay, everybody good with this? All right. All right. So that's what we're going to do. Now, our job now is to come up with some kind of a quantitative way, something called the equilibrium constant, to be able to calculate and describe the equilibrium. Okay? All right. Let's do the derivation first of all of Kc. That's all we're going to get to today is derivation and setting it up. We're not actually going to use it a whole lot today, but we will be by tomorrow in the lab. Well, yeah, tomorrow will be your lab.
Yay.
Okay? Assume you have this equation. Where A, the small letter A and the small letter B, the small c's, they represent the coefficients in the equation. And the large A, B, and C, and D represent the sodium, chlorine, whatever it is. Okay? All right. This is, you got to follow me here real well because I'm going to refer back now to what we learned in kinetics. Okay? Assuming a one-step mechanism, can you tell me what the rate law expression would look like for this equation? If this were only happening in one step, then that is the slow step. The only step it is, right? Got it? So, if that's the coefficient and that's the coefficient, it tells you how many times it's using the slow step. What would the rate law expression be for the forward direction? We all agree it would look like this. Rate forward would equal Kf A to the A, B to the B. Because the A's and the B's are the coefficients, how many times you're using the slow step, right? Now, I know if you understand this, you can tell me the reverse rate law expression. I think you probably can. What would the rate law expression be in the reverse direction if I were looking at it that way?
Same thing, just C's and D's.
Exactly. Rate would equal KR. We'll call it KR because it's not going to be the same K. It's going to be a different reaction. C to the C, D to the D. Where little c and little d are the coefficients of these guys. That tells you how many times they're used in the slow step. Because it is a one-step negative. By the way, in a derivation, I'm trying to, I want you to write down these little sentences in here to explain it. I always hate it. I don't know about you guys. You probably had some derivations in calculus, in physics, right? You probably had some derivations. Maybe even in, I don't think they're the same kind of thing like in geometry or in math class, but you know what I'm talking about. Well, one of the things about chemistry is the derivations aren't just mathematical, they mean something. As you're going to see when I get done with this, I'm going to show you how to use this to predict things about the equation. So you kind of have to explain what you're doing. Next explanation I need is this. What happens at equilibrium? What can I say at equilibrium happens to the rate forward and the rate reverse? What are they? They're equal. At equilibrium, the forward and reverse rates are going to be equal. That's the definition of equilibrium. Well, if this equals that, right? Y'all look it up here? If this equals that, then can't you just as well say that this whole thing here equals that whole thing there? Yep. Exactly. Now, where am I going with this? Well, remember what we're trying to do? We're trying to derive. Lizzie's trying to get her deriving license, but that ain't going to happen. We, at least, can derive KC. She may not be able to drive a car, but she can derive a KC.
Oh.
Poor Lizzie.
Wow.
What time's your thing today? We'll be praying for you. 3:30. Everybody remember to say a prayer for Lizzie because she needs it. And she's running out of counties to take her driver's test.
There is a lot of more driving licenses.
There's a lot of more.
she's looked them all up. She knows how to get to every one of them.
She's got a checklist.
Clearfield's next.
All right. Well, she really does. She really does this up. It's terrible. All right. Now, here's what we're getting to. We're trying to get to this new constant. I told you to use lowercase k for rates because we're going to use a large K for equilibrium. We're going to bring all of our constants to one side and all of our variables to the other. So if I bring the KR over to the left side and I bring the variables over to the right side, what will they look like on the right side now? C to the C, D to the D, over A to the A, B to the B. In other words, the products raised to their coefficients over the reactants raised to their coefficients. That is KC. That is your final answer. Now, a lot of you guys, again, if I left it right there without saying this next thing, I think you probably wouldn't quite understand exactly why we did this. Let me tell you why we did it with this last little thing here. If I look up Kc for an equation, if I calculate Kc for an equation, I find that Kc to be a large number. Let's just make up a number like 1,000. Okay? What does that tell me about the rates? In order for this number, this ratio to be 1,000, who has to be bigger, the numerator or the denominator?
Numerator.
The numerator. So that means the forward rate is way better than the reverse rate. And that's one of those cases where if I put in, 4 moles of this and 4 moles of that, if I got a large Kc, when I finally end up my products, I'll end up with like 3.99 moles of this and 3.9. I'll get mostly product. If, on the other hand, I look up Kc and he's 0.0001, what happens there?
Bottom's greater.
Yeah, it means the bottom number, the denominator, has got to be bigger. The reverse rate's way better. So that reverse rate being way better than the forward rate, I will reach equilibrium very quickly, and I'll only use up. I put 4 moles of this in and 4 moles of that. I might only get 0.001 moles of that, 0.001 moles of the other guy. That's what Kc tells you. That's the point of Kc. All right. Hopefully you understand that. Even if you don't, we're going to be calculating them and setting them up today and the rest of the chapter. But let me just say one more thing about this before you do. You have a question? Oh, I'll tell you. One more thing about this, I'm going to kind of bring it home with you. How I could have. This is what happened with Shania. I know. This is where I dropped my pencil and screamed.
Yeah, we heard
All right. Look at this point, I'm going to have you guys do those problems for homework. You know what those problems? I even said this. I did all this, including what I'm about to do now. So if I've got sodium plus chlorine yields sodium chloride, and there's your equation, right? If I wanted to set up the equilibrium expression for that equation, it's not an equilibrium problem, by the way, but if it were, what would it look like? What would Kc be for that problem? It's the products over the reactants, right?
Yeah.
So wouldn't it be Na with Cl raised to the second power over Na what? To the second what? To the first, right? Everybody agree? It's products over reactants. Okay. That's all you have to do for these. It's going to take you about 10 minutes or 15, maybe however much time you have left in this period, to do that. All right?
And tell us what Shania did.
She did the equivalent of this. She put the reactants over the products and she smashed them together. No idea. No idea. I know. She had reactants over products and she smashed the two of them like it was like sodium plus chlorine. She put the sodium and chlorine together.
And it's your fault.
And it was my fault. Exactly. I take full responsibility.